Ever wondered how capacitors store energy? Or what makes one capacitor different from another? Well, let's start at the beginning. A capacitor, in its simplest form, is an electronic component that can store and release electrical energy. But how does it do this? The secret lies in something we call capacitance. Capacitance is the ability of a system to store an electric charge. It's determined by the physical characteristics of the capacitor, specifically the surface area of the conductive plates and the distance between them. The larger the surface area and the closer the plates, the greater the capacitance. Now you might be wondering, what's between these plates? Well, that's where the dielectric comes in. A dielectric is an insulating material that separates the two conductive plates. It not only prevents the flow of direct current, but also stores electrical energy in an electric field. The conductive plates, on the other hand, are called electrodes. These electrodes are where the electrical energy is stored. When a voltage is applied, positive charges accumulate on one plate while negative charges accumulate on the other. This separation of charges creates an electric field within the dielectric, and voila, energy is stored. But here's the thing, not all capacitors are the same. Their performance and characteristics can vary greatly depending on the materials used for the dielectric and electrodes, as well as their physical design. For example, some capacitors can store a lot of energy but release it slowly, while others can store less energy but release it very quickly. So that's the basic framework of a capacitor. But there's more to it, isn't there? Different types of capacitors, perhaps? Indeed, capacitors come in multiple types, each with unique properties and applications. First up, we have electrolytic capacitors. Known for their high capacitance, they are often used in power supply filters. However, they do have a downside. They're polarized, which means they can only be connected one way. Next in line, we have ceramic capacitors. These little guys are non-polarized and are typically used in high-frequency circuits due to their small size and excellent temperature stability. Thirdly, we encounter tantalum capacitors. With a higher capacitance per volume than ceramics, they are often used in space-sensitive applications. Moving on, we have film capacitors. These are non-polarized capacitors that are reliable, stable, and have good high-frequency characteristics. Lastly, we have variable capacitors. These are used in tuned circuits, such as radio receivers, and their capacitance can be changed by adjusting the physical spacing of the plates. These different types of capacitors find their uses in a variety of applications. Let's delve into that next. Capacitors are incredibly versatile and find use in many areas. Let's start with electronic circuits. Capacitors play a crucial role in these circuits, smoothing out power supply voltages and filtering out unwanted noise. They're like the bouncers of the electronic world, keeping everything running smoothly and making sure no unwanted fluctuations crash the party. Next, we have power factor correction. In alternating current power systems, capacitors correct the power factor, making it closer to 1. This increases the system's efficiency, reducing energy loss and improving the stability of the power grid. On to filtering. Capacitors are the sieve of electronics, filtering out frequency components in signals and power supplies. They're like a coffee filter, letting the good stuff through while keeping out the undesirables. In timing circuits, capacitors, in conjunction with resistors, create time delays for processes like blinking lights or timing intervals. Finally, in energy storage systems, capacitors store and release electrical energy quickly, like a sprinter bursting out of the blocks. Capacitors are not just diverse in types and applications, but also carry unique properties. Each capacitor carries its own set of properties that define its functionality. Let's delve a bit deeper into these properties. First off, the voltage rating. This is the maximum amount of voltage a capacitor can withstand before it fails or breaks down. Exceeding this rating can lead to catastrophic failure. Next, we have the capacitance tolerance. This is the percentage by which the actual capacitance can vary from the nominal or stated value. The third property is the leakage current, which represents the small amount of current that leaks through the capacitor, even when it's fully charged. Then there's the equivalent series resistance, or ESR. This is the sum of all resistances in a capacitor's equivalent circuit. Lastly, we have the temperature coefficient. This property defines how the capacitor capacitance changes with variations in temperature. These properties are often depicted through symbols and diagrams. Let's have a look at those. Capacitor symbols and diagrams are essential for understanding their operation in circuits. Let's delve into the world of symbols and diagrams. Schematic symbols are like the alphabet of electronics. They represent various electrical and electronic devices or functions, such as wires, batteries, resistors, and of course, capacitors. Now, circuit diagrams, these are the sentences formed by our electronic alphabet. They illustrate how components are connected together electrically in a system or a circuit. In these diagrams, capacitors are often represented as two parallel lines, symbolizing the two plates of a capacitor. Now onto polarized and non-polarized capacitors. Polarized capacitors, like electrolytic and tantalum capacitors, have a positive and a negative electrode. Their symbols usually have a plus sign indicating the positive side. Non-polarized capacitors, on the other hand, like ceramic or film capacitors, can be connected in any direction. Their symbols lack the plus sign. Now let's move on to the process that capacitors are most known for, charging and discharging. Capacitors undergo a fascinating process of charging and discharging. Let's dive into this process. In an RC circuit or a resistor capacitor circuit, the capacitor charges up by accumulating charge from the current flowing through the resistor. The rate at which it charges is determined by the time constant, which is the product of the resistance and capacitance in the circuit. The charging curve of a capacitor is an exponential rise, starting from zero and eventually reaching a maximum value, the supply voltage. Conversely, the discharging process begins when the circuit is broken. The stored charge in the capacitor starts to drain out, following an exponential decay curve. The time constant remains the same, guiding the rate of discharge. Visualize a bathtub filling and emptying with water. It's a fitting analogy for the charging and discharging of a capacitor. From the basics to the charging process, we've covered a lot, but capacitors have more advanced topics and uses too. Capacitor technology is ever evolving, with newer types of capacitors being developed. One such advancement is the supercapacitor. These powerhouses go above and beyond traditional capacitors, storing a significantly larger amount of energy. They're particularly useful in applications where a large amount of energy is needed in a short time. Now let's touch on different capacitor technologies. These include various materials and designs used to enhance performance. For instance, some capacitors use high permittivity dielectrics for increased capacitance, while others may use low-loss materials for high-frequency applications. Next up, nanocapacitors. These tiny capacitors offer high capacitance in a small footprint, making them ideal for use in miniaturized electronic devices. Last but not least, pseudocapacitors. They bridge the gap between supercapacitors and batteries, offering high-energy storage like batteries and quick charge-discharge capabilities like supercapacitors. Testing and measurement is an essential part of working with capacitors. Let's discuss that next. How do you know if a capacitor is working as it should? You test it. In the realm of electronics, testing is not just a good practice, it's a necessity. A multimeter is the Swiss Army knife of electronics, capable of measuring voltage, current, and resistance. But when it comes to capacitors, we're interested in its capacitance, right? That's where capacitance meters come in. These specialized devices measure the charge storage capacity of a capacitor, giving us its value in farads. Now, what about equivalent series resistance, or ESR? An ESR meter measures the internal resistance within a capacitor, which can affect its performance. The lower the ESR, the better the capacitor can handle higher frequencies. But testing isn't just about the right tools, it's also about the right methods. There are several ways to test a capacitor, each with its own advantages and drawbacks. From simple voltage measurements to complex waveform analysis, the choice of method depends on the nature of the problem at hand. Capacitors have come a long way and continue to evolve. Let's take a sneak peek into the future. The future of capacitors is exciting and full of potential. As we look towards the horizon, we see an array of innovative trends shaping the landscape of capacitor technology. One such trend is the exploration of new materials. Researchers are delving into exotic materials like graphene and other nanomaterials to unlock unprecedented capacitance and efficiency. Another trend is miniaturization. As electronic devices become smaller and more powerful, the demand for compact capacitors is on the rise. Think of a capacitor that fits on the tip of a needle, but can power your laptop for hours. Moreover, capacitors are also evolving to meet the increasing demand for high-frequency applications. These high-speed capacitors will play a key role in the next generation of communication systems, enabling faster data transfer and smoother performance. Lastly, we're seeing strides being made in improving energy density. This means capacitors will soon be able to store more energy in a smaller space, revolutionizing energy storage systems. Capacitors, as we've seen, are fascinating devices with immense potential and a bright future.